Welcome to Systems Philosophy. In this episode, I want to focus on dynamic equilibrium. It's a concept that's easily spoken, but I want to get you to internalize and understand it in more depth. By dynamic equilibrium, I mean a system that returns to a set state under corrective forces. From that perspective, if you roll a marble into a hollow, the marble will undergo a form of dynamic equilibrium where it sort of rolls backwards and forwards until it settles somewhere near the bottom of the hollow. Same with the ball. If you take a pendulum, a weight on a string, and swing it, it will swing backwards and forwards around the centre mass of the earth and then eventually come to rest. If we had an imaginary pendulum with no friction or wind resistance, it would continue to oscillate around that center point. That is an ideal harmonic oscillator that's in dynamic equilibrium. The dynamic in this case is simply the forces of physics. Nothing more intelligent is applied. If we take the idea of a pendulum and we turn the string into a stick, something solid with a weight on the bottom and perhaps a pivot point on the top, we can get the same equilibrium that we just described, where we swing it and it eventually comes to rest thanks to friction and wind resistance. If the wind blows to move the pendulum, then eventually it will come back to rest, balancing the force of the wind and the force of gravity. That is a sort of dynamic equilibrium because the wind forces are more variable in the physical world than the force of gravity, which itself is variable, but it's variable over much longer timescales. Taking that pendulum example, if we now invert the pendulum and balance it on the bit that was swinging, we now have an unstable dynamic equilibrium with a stable spot where the forces exactly oppose gravity. Anyone who's tried to balance a broom on the end of a broomstick will understand what I mean. You've got to move the bottom of the broomstick fairly aggressively to maintain the sweeping part of the broom at the top, and if you're very careful, you can balance it that way. We see examples in nature where balancing rocks have maintained a sort of unstable equilibrium. That's not dynamic. The example of the broomstick is dynamic because the movements of your hands are actively correcting and ensuring that the head of the broom doesn't fall down into the more natural, stable equilibrium state. This form of corrected self-dynamic equilibrium is also present in the candle flame. The shape and wick of the candle are designed specifically so that the candle burns in a dynamic equilibrium even as the wax is consumed, and even if it melts down the side of the stick candle, if you like, or forms a pool. The dynamic equilibrium changes. I've had big candles, sort of fat, long burning candles with short wicks where the wick itself starts to burn and the flame shrinks. So you can see the equilibrium point drifting from where you first light the candle until the candle has been burning for a while. You will also see the solid wax start to build a wax pool that sometimes forms a level lower than the candle wax around the outside. And so we have a sort of engineered system that's designed to produce the flame consistently, that undergoes dynamic equilibrium between combustion, which happens as the melted wax under capillary action soaks into the wick and then combusts from there as a liquid interacting with the surrounding air. And if you look at the candle flame, you'll see exactly the pattern that's going on. You also have the dynamic equilibrium of convection, which is driven by gravity. So the classic teardrop shape of the candle flame is different to the spherical shape of a candle flame burning on the space station in zero gravity. That's caused because the heated air from the candle rises and cold air comes in from below and the sides to replace it, causing a convection cell that affects the candle flame. And if you use an infrared camera, you'll see that there's a trail of rising heat above the flame. It also makes the combustion under gravity more efficient than the combustion without gravity, because without gravity you lack the active introduction of oxygen into the wick. These are all forms of physics and dynamic equilibrium without living systems. We have things like thermostats that are designed to maintain a sort of dynamic equilibrium in the temperature of a shelter. Thermostats usually have upper and lower set points, and depending whether you're heating or cooling, one set point will switch on a heating or cooling circuit and the other set point will switch it off. What you get then is you get a wavy form of dynamic equilibrium, a cyclical. Let's take a fridge, a refrigerator, a refrigerator. It makes the air cold again. That's the name. And the temperature gets above a certain set point of the thermostat. The thermostat switches on the compressor, which cycles the refrigerant through its condensation phase and pumps it through whatever physical means is designed to create a cool zone. That cool is then used to cool the space, and there's lots of technologies for fridges. I won't get into that. And once the temperature has dropped below a certain point, the compressor shuts off. There is still a little bit of overshoot as the cool that has already been generated in the cooling circuit is transferred into the storage space. And then there is the dynamic that heats the storage space as the refrigerator loses heat through its insulation or loses heat more quickly as people open and close the door. There is a dynamic between the air in the refrigerator, which has very low heat capacity, the structural materials in the refrigerator, which also are highly insulating, at least on the wall. Shelves and things not so much. Metal has some heat capacity. And then in the things that are stored in the refrigerator, which have higher heat capacity. So the cycle period itself changes, as does the frequency. For instance, if you take an empty refrigerator and turn it on, it won't take as long to cool down as a full refrigerator at room temperature that's turned on, because you're having to absorb a lot more heat into the things that are stored in the refrigerator than the empty refrigerator would store. So we see the simple thermostat circuit dynamics change considerably depending on the physical conditions. If you take something cold out of the refrigerator, it doesn't change the internal temperature, but it might change the cycling frequency because you have removed a thermal drag, a thermal anchor, a thermal battery storage medium from inside it. Therefore, the temperature will fluctuate more readily. The compressor may not run as long, and each cooling phase may not take as long. If you put something at room temperature fairly bulky into the refrigerator, like after a shopping trip, you get the opposite effect. You get warm items introduced into the cold space that exchange their heat with the air and the surrounding environment. Convection, radiation, conduction, that's the three mediums of heat exchange. And the thermostat will pick up that exchange and then cycle accordingly. So what typically happens is that a fridge that has been sitting at equilibrium, you've been away, everything's fine, the temperature has settled down to a regular cycle, you've opened the door, cold air has fallen out, warm air has been introduced, and you've loaded up a lot of shopping that's been sitting in the car or your bags and is warmer than it was. So there is extra heat now to be extracted, and the dynamic equilibrium of the circuit has changed reflexively compared to the environment. The refrigerator also interacts with the environment. So if the heater is turned off and things get cool overnight and nobody uses the refrigerator, then the motor will cycle less often because the thermal gradient between the inside and the outside that is being insulated by the walls of the refrigerator has become reduced as the heater is either turned down or turned off overnight, depending on your heating practices. If the heater stays at the same temperature all night, then what will have changed is the pattern of door openings, which itself will change the cycling. So we have this reflexive dynamic interaction between a technological item, that is the refrigerator trying to keep the food between the set points of the thermostat, and the environment in which it operates. I'm using this example because I've been leaning heavily on living systems and biology. I want to point out that these dynamics are just as applicable to technological systems and technology. There is a caveat here in that the technology is reliant on non-living physics and in some cases quite simple electronic control circuitry that could be manual. For instance, some hot water systems don't use electrical thermostats at all. They use bimetal thermostats that control valves on pilot flames. And therefore you can have a fully non-electric thermal control system that is still running using similar characteristics to what I've just been through with the refrigerator. Only in this case we're talking about a water heater where you have some sort of heat source, which could be natural gas, and some sort of control mechanism. This, like the ship of Theseus, still requires maintenance, people. The thermostat in the hot water system and in the refrigerator will keep working for as long as the reliability of the technology and the energy is supplied. At some point, if that runs out or fails, then we're back to basic physics and the control system is broken. With human intervention, we have recreated the sort of unstable dynamic equilibrium that we create by balancing the broom at the handle, and that life has created. However, we can get into theological conversations about where life actually came from, even on top of the scientific discussion about whether it came through a natural self-assembly process on Earth or whether it was assembled somewhere else on the solar system or the universe even, and was seeded into our solar system and our planet. That is the far reaches of philosophy that science hasn't yet properly touched. And some of the experiments are interesting but inconclusive. If we manage to construct a living cell, which we're making progress towards, in many ways that doesn't answer the Genesis question, because we would be doing the same that we've done to our technology. We've reproduced something existing, but the secret source has always been the living being that engineers the technology, ourselves. So the initial genesis is still a mystery to be discussed philosophically, to be debated scientifically, and to be explained in some ways using the systems philosophy. My channel tries to remain science adjacent, so I lean more on science than I do on theology, although I don't dismiss theology. Okay, I thought I would spend an episode away from strict biology, even though, as I've just pointed out, it's difficult to separate systems philosophy from biology without going directly into physics, which I can and probably will in later episodes. The physics requires more specific background and is not as generally applicable, and also somewhat speculative. Most of us are familiar with the sort of dynamics that I'm describing. Dynamic equilibrium is trying to maintain something around a set point. That is done through some sort of feedback and control mechanism. That's the basis of cybernetics. Cybernetics need not be based around electrons. There is a genre in steampunk that thinks about clockwork cybernetics, a sort of a non-electronic age alternative to how a highly advanced society could have solved the same problems that we have solved with electrons. That's why I touched on the water heater example, to show that it's not only the electron. We can talk about physically coupled systems having behaviours. The physically coupled systems work because of their structural relationships, the way that they relate to each other. Unless the ship of Theseus is constructed in the way that it is, with planks and sails and masts and ropes and pulleys, it will not work as a sailing ship, a means of transporting goods and people across the ocean. Unless a thermostat is constructed with the heat pump or the heating mechanism and the storage system and all the components that make up a hot water system or a refrigerator, then the dynamics won't work. So we are looking at form and structure as both being important components in the material world. One of the weaknesses of the Greek philosophy and knowledge, thinking perspective that Western thinking has inherited is we are very materialist. We don't consider the structure as primary. We consider the structure as something that's made out of materials. A refrigerator can be constructed out of many different materials. The atoms in a refrigerator can be arranged in many different ways, but only a very few will form a refrigerator. Most of them will form a piece of junk, something that doesn't perform the function of the refrigerator, which is why we need to maintain the structured systems. This is one of the very important philosophical points that I wish to tease out and come back to as a touchstone in systems philosophy, separating the material things, the water and the materials that make up the human body, from the actual structure of the human body, which is an incredibly fine, structured, evolved nanomachine, if you want to think of it in purely materialistic form. This is part of the framing and paradigm that I'm also using as a theme throughout these episodes. So for today, our focus has been on equilibrium, dynamic equilibrium, harmonics, feedback systems in both living and non-living systems, showing that a purely materialistic point of view is not enough. We need to consider the relationship and the system's dynamics as we view the world around us. Thank you for watching.